Hello everyone. My name is Radha Gidsuri. I work at AMD. I'm also a Chronos working group member. We put together this session just to bring up everybody up to speed with OpenVX, and we just launched OpenVX 1.2 press release at Embedded Vision Summit. And we have a very packed session today, and we got a lot of speakers. Here is the agenda that you can see. So we got very tight schedule. So we would want to. We have a lot of breaks in the middle during the morning break and lunch break, so you can feel free to contact us. You see Frank at the back, his red shirt, he's our chair. So you can just ask all kinds of hard questions to him. So let's get started. The morning session is all about OpenVX 1.2. We're going to talk about all the features that are there. There's going to be a hands-on tutorial. Tomer is going to give a presentation about neural network extension. He has a wonderful example of AlexNet, and that's going to be a great example, showcasing neural networks and the power of OpenVX in there. And after that, Thierry, who is unfortunately could not be here, but he's with us. He's going to be presenting about import-export from France. So he's on us. He's online with us. And Jesse is going to talk about safety-critical component of OpenVX, and that's going to be a wonderful part of it too. That also we released our latest spec. 1.1 recently. That's the morning session. In the afternoon session, we're going to talk about OpenVX roadmap. Frank is going to come back and he's going to tell us what to look for in future. And then there's going to be a presentation about NNEF, another standard from Khronos. It's still under development, about neural network exchange format. And after that, Andrew is going to give a talk about SQL and in the context of computer vision, acceleration, and OpenVX. He's going to give a talk about that standard. And then after that, there's going to be a small break, and then we have 6 vendors who would like to come and talk about their implementations of OpenVX. So this is a fully loaded session. So let's get started. I would like to invite Frank to start the session with his ecosystem overview of OpenVX.
Thanks everybody for coming. Again, my name is Frank Burrell. I work at Cadence, and I chair the OpenVX working group. I'm just going to give you kind of an overview of where OpenVX sits amongst some other Chronos standards, and also mention a little bit about OpenCV and how this OpenVX thing contrasts with it. So let's start with Chronos. So Chronos is an industry consortium with dozens or hundreds of members. I think I have a slide, next slide, with all the membership. But the idea of Chronos is to provide an API or APIs that provide a uniform interface to a lot of different kinds of hardware. So the hardware may be different kinds of GPUs or CPUs or DSPs or special purpose hardware, FPGAs, and we want to be able to provide a common interface to those so that application developers don't have to write specific code for every different kind of platform. And OpenVX is one of those. Many of the Chronos standard APIs have been very successful. We've got over 1 billion people using Chronos APIs every day, and we hope to be able to say the same soon about OpenVX. And here's your eye chart with all of the current members of OpenVX, of Chronos. I think I have a slide later that shows a good number of these folks, and especially even a good percentage of the promoter members actually have implementations that you can run on their hardware. So here's a view of several of the important Chronos open standards. So of course we have OpenVX over here on the left. NNEF will get another presentation later, but the idea is for computer vision, obviously everybody's using neural nets. When we want to connect that to some more traditional imaging vision processing, and so NNEF is a way to sort of describe a neural network, and I'll talk about the roadmap later, but the idea is that would eventually be imported and connected to an OpenVX graph for efficient processing. So you got those vision stuff over there on the left. On the top, there's a lot of web APIs for, a lot of times they're web interfaces to some of these other APIs that you would run on a local hardware. On the near side, on the right, we have the graphics APIs, and of course these are running on, if you have a phone, it runs on your phone. So there's a lot of success with these graphics APIs. And then down below is parallel computation APIs and file formats. And I don't want to say too much about that because there'll be a presentation later. And moreover, these guys here know way more than I do about this stuff. So like, I can tell you about this. But the idea is these OpenCL is in general a language that you can use to implement some of these functions, whereas OpenVX is a library of provided functions for you that you can just use. And in some cases, you could use OpenCL to implement OpenVX, and some implementations do that. Just very quickly about OpenVX, you'll hear a lot more about it, but it's a very high-level API in terms of you describe your algorithm at an abstract level where you say, I'm going to do this kernel followed by this kernel, and you actually build up a graph, which is a description of your entire image processing chain. And the reason that you do that, the reason that it's designed that way, is so that it can be mapped to lots of different kinds of hardware. So every different kind of hardware is going to have a different memory model and a different strengths and weaknesses in terms of where it wants to compute things and how. But if you say your algorithm, you describe it abstractly, you have at least the opportunity to map it efficiently to each of these kinds of hardware. And it's up to the vendor that provides your implementation of OpenVX to make sure that it is, in fact, efficient on that hardware. And that's what we mean by performance portability. We don't mean that it's the same performance on every device. We mean that it's running efficiently, and somewhere close to the entitlement or a theoretical maximum performance on that device if you run using this OpenVX library. And the other thing about it, in addition to being portable, is that it's meant for low power domains. So things like most of the computation is in fixed point, not floating point. Your pixels are going to be 8-bit or in some cases 16-bit. And so we make sure that that's supported. Everybody has to support that sort of low power 8-bit stuff. And you don't necessarily, because the functions are sort of well defined, it's potentially you could actually have an accelerator for each one, and you could just build up your graph and say go, and you could even shut down the CPU and GPU and anything that's doing a lot of high power computation or consuming a lot of power. So I'm going to stop there and let the other guys talk more about it. This is showing sort of the evolution over the, I guess, the last few years of the implementation. So OpenVX 1.0 came out in 2014, and you can see that I haven't counted them, but it looks like 10 different actual implementations that have passed the conformance test. So that's another thing about this thing is that it's not just a collection of functions. There's a set of conformance tests that make sure that you've implemented all the functions and you've done it right. You get the right answer and the same answer as everybody else gets when you write your code. So there's the 1.0 version of the spec, the first one. The 1.1 version, we've got several new implementations here. My company Cadence, Imagination, Texas Instruments have all passed. And these companies have all passed the 1.1 version of the conformance test. So this is, and you can go to the website and see all these different specs as they evolve. The 1.2 was just announced at the beginning of this week, so there's no compliant implementations yet. And in fact, actually what will happen is there's a sample implementation, which actually it just runs on a PC, and it's not meant to be performant or optimized or anything, but it's functional. So there'll be that available for download on the web, and the conformance tests will be available. And we expect that all to be done in June. And then we'll start to get submissions for people who can actually conform to the latest version of the standard, which you'll hear about today. And I'll have a couple of slides later today about new stuff that we're going to do. I already mentioned NNEF. The other thing here is just mentioned on this slide. Right now, we have a functionality for user kernels, but those user kernels run on the host. They run on a CPU, and you write them in C. And so we're looking for a way to all of our customers, speaking for my company and I think for most companies, our customers want to be able to write optimized code on the target, and so we need to provide a way to do that. So that's sort of the history here. I mentioned 1.2 just released, which you'll hear about more. Just a little bit about OpenCL. OpenCL is a language for writing code for heterogeneous parallel resources. And so it's fairly low level in terms of, I mean, you know what the memory model is. You know what all the resources are, what they can do, and what their strengths and weaknesses are. And you have complete control, which is great if that's what you want. But it's not necessarily great if you want to be performance portable, because what you'll do is because you know about this hardware, you will write code specific to it and optimize it. But what you can do is actually have, say, OpenVX, which is more abstract, and you sort of compile to your graph to OpenCL, and it could give you an implementation that way. There's a number of ways that you could have OpenCL and OpenVX interact, and I think you'll hear more about that this afternoon. So here's sort of the ecosystem here. You've got your application on the top writing to OpenVX using a graph. And that OpenVX could be, as I just now said, actually, implemented in OpenCL or C or C++ or some combination of those that go to your programmable vision processor. But you could also have actually dedicated hardware because we've defined exactly what these functions are supposed to do. And you have, say, registers to modify the behavior a little bit, but you could create very efficient hardware. Let's see, and yeah, I think that's all I'm going to say about that one. This is a bit of an eye chart, so I'm just going to point out a couple of things. So we've got OpenVX and a number of aspects of OpenVX here contrasted with OpenCV and OpenGL. So I think everybody here has probably heard of OpenCV. It's very popular. Everybody's using it in academia, and even in industry, it's a good starting point. A lot of people do a lot of their development in OpenCV. It's a huge library with thousands of functions. So the thing about it is that when people actually go to deploy, say on an embedded hardware, they'll take some portion of that. First of all, there's probably not there is not a single version of OpenCV that runs on multiple kinds of hardware. What your hardware vendor will do is he will get some subset of it and optimize that, and that's what you got. And then so what you'll do is you'll take that, and then you'll optimize more for that platform. And so what you have is non-portable code while you're done. So that's sort of the difference here. We've got a smaller set of functions for OpenVX, but it's growing. We've added some with 1.2. We'll continue to do that based on feedback from the community. But the benefit that you get from that is that you get this portability and even performance portability. And I talked about OpenCL. I think the other thing I'd say is well, I mentioned the conformance test. Like there's no conformance test for OpenCL, or OpenCV. So if you ran your code on one machine and ran very similar OpenCV-like code on another machine, you might get different answers. So that's what you're looking for with this conformance test. And actually OpenCL, the language, also has conformance tests for it. I think I'll stop with that one. And I'll mention also here safety critically APIs. So the idea here is that you're running on you're doing self-driving car or some other thing that actually has actuators in the world that might kill people. So you need to have a lot of high confidence in your code, and so there's a lot of procedures that are defined by the automotive aerospace industry for how you do that. And so there's a version of development right now on these are graphics APIs up here. There's also a released spec as of actually the beginning of this week again for a safety critical version of OpenVX, and the idea there is that you instead of building your graph sort of at runtime at the beginning every time you start the car, you build your graph and then you save it. You compile it and you save it, and then when you start the car, you just load it and run it. And so all you really need is a very light runtime, and that is all that runs on your car. And it enables you to sort of do, it's MISRA compliant for all the APIs, and you can do this thing with all static allocation of memory and stuff like that. So it's divided the API into those pieces. And I think you'll hear more about that later today. Is this? And there's some additional work going on right now for early work about, there's Vulkan being discussed for safety critical, and also there's this safety critical advisory panel that sort of feeds into all of these. These are Chronos groups here. That's my last slide. So obviously there's going to be a lot more detail about everything later today. I don't know if there's any high-level questions. If not, I can hand back. Is it over to you? Yeah, sure.
So I think 2 days ago, a person from Google talked about putting TensorFlow on a core-form DSP.
Yeah.
Mm-hmm. It seems to me that it is serving some purpose of OpenVX as well. So I'm just wondering, moving forward, would you consider some collaboration?
So we've been talking with the TensorFlow folks since the beginning of the NNEF effort, well, the thing about there's TensorFlow, there's Caffe, now there's Caffe 2, there's Torch, there's actually a bunch of others that, and so that's part of what NNEF is trying to do, and sort of have a common way to describe these networks that could then be, both read and written by TensorFlow and optimized by hardware vendors. So that's sort of, I would say, the main thrust of what we're doing is because we want to be able to support not just TensorFlow, but lots of other things. So TensorFlow has its interface, and Caffe has its interface, and so anyway, we're trying to sort of, our job as a standards body is to try and bring that together. The other thing that we have is, and you'll hear about here in just a few minutes, is this neural network extension. So the idea there is you could potentially have a tool that translates from whatever Caffe or TensorFlow or other whatever format they want into calls to this this API that you'll hear about later. So right now it's we're dealing with just like translators from one to the other. When we get to NNEF, hopefully we'll have a common language we're all speaking. Other questions? All right, thanks. Well, I'll turn it back over to Radha.
Thanks, Brian. Is that okay? Hello, everyone. I'm back again. My name is Radha Girturi, those of you who joined late. So I'm going to just quickly go over various features of OpenVX. I'm going to briefly touch upon them because there are a lot of features. To going over that, it's going to be a long presentation, and we have a lot more exciting presentations following mine. I just want to give you a link here, chronos.org/registry/VX. That's where you can find all our specifications, header files, and there's also a forum on Khronos. If you have any questions after this session, feel free to post questions, and a lot of our working group members, they'll try to respond to you if you have any specific question. And also, if you have any feedback about our spec that you want to see, or if you have any particular functions that you guys want to see, feel free to post it on the forum. So let's get started. I think Frank briefly touched upon this idea of graphs, and which is a key feature of the OpenVX. This is what lets a application to describe the whole workload as a kind of a data flow going from input to the output. And what it enables now is for an implementation to look at the whole workload, try to see what it can do to optimize it in terms of assigning work to various different hardware that is available on the SoCs or whatever the system it is, right? It was initially designed primarily for low power embedded, but that doesn't mean the spec is limited to that. It means in theory, you can take the same idea and use it on any hardware, right? You could go to the extent of running it on a server, right? Conceptually, that's the same, but I think for our focus is going to be mainly on the embedded for this talk, right? Now, how does these graphs get us the efficiency in OpenVX? First thing to look at is you can take a graph workload and try to split the workload into pieces. Try to see, depending on each piece, which hardware is more efficient to run that workload on. You can try to schedule it, and also you can try to check to see if there are two works that can be run in parallel, and if you have two separate execution units sitting in the hardware, you can try to schedule it. And all this work can be done by an implementation. This is kind of one way to optimizing, looking at a graph. And the next one is the memory management. If you try to look at how people optimize at low level, they try to squeeze, try to get the memory as low as possible. It's a lot of optimization, hand coding happens. What OpenVX allows you is a means to specify intermediate buffers as kind of a abstract buffers and as an intermediate buffers, so that implementation can just look at those buffers and say, these are some buffers that application is not going to access it on the host. That means it has liberty to allocate buffers and reuse buffers at as much as possible, and which gets you the next level of optimization. So there's a lot of memory management done, which kind of offloads the work of a developer. And sometimes it's even better because the underlying implementer knows a lot more. Generally, they don't expose those features. Now, what OpenVX allows the implementers to do is take those advanced features and then give that to the application use cases here. Now, in addition to just getting a better memory utilization, you can also think about some functions in a graph. Let's say you specify 2 functions. Somebody be able to fuse those kernels. If you try to look at some of the implementation, for example, we have our AMD implementation on the GitHub. We have a code generator that comes. It just looks at the graph, tries to see what are the functions that can be combined together. It tries to generate one OpenCL code combined, right? I'm sure a lot of implementers have very similar kind of ideas in there. So you can take this. An extreme example of this is I just created one skin tone detector, which is nothing but just comparisons, greater than, less than, getting out, doing color conversions, things like that. You can see the output is going to go to the extent of using 1-bit values. So there's kind of a lot of flexibility that an implementation has to be able to fuse these kernels and try to get a lot of performance out. You can kind of think another way as you're using registers level of memory allocation in one way. Instead of reading buffer to buffer, just loading into the register, just using the same register going forward. So you get a lot of performance coming out of it. Now, and one more thing, especially from my experience, old experience with DSPs is, you try to pull data into the local memory and try to use it. So tend to process tile by tile. Instead of going from one function at a time, you try to take one tile, process the whole pipeline, take another tile, process the whole pipeline. Right? So all these things are possible by an implementation once you describe your whole workload as a single graph, as a data flow, and give it to the implementation. Implementation will spend some time analyzing the graph and try to see what all it can do, and it will kindly create some kind of an intermediate execution binary that it kind of at runtime keeps executing to get the key performance out of that. So next, I'm going to just show you a couple of examples just to get a flavor of how these graphs are going to look. The first one is a simple corner detector example. Imagine you have an RGB image coming from a camera, and you want to kind of just find corner points in there, key points in there. So we're going to just run simple Harris corner to get it out. So a few terms that I'm going to introduce here. So one is the VX context. So you see all the objects in OpenVX are all kind of opaque data objects, basically opaque objects. So all the objects are going to stay within a context, which is very similar to what OpenCL uses. So you allocate each buffer within one context of OpenVX. So you have a VX context that kind of is the world of your application in one way, as far as OpenVX is concerned. And you have other objects that you can use. For example, image. There is a VX underscore image. It's kind of an append object. You kind of describe what image is it, what are the dimensions of the image, what is the format, is it RGB or IYUV or 8-bit or 16-bit, you can describe that. And also, if, for example, for data such as key points, where you want just locations of X and Y and some additional parameter about what these key features are, such as strength of the corner. So you have something called an array, and where you can specify, I want an array of a particular type. And in this particular case, we're going to use a key point array, which is going to basically have X, Y values and some kind of additional parameters about that key point in there. So let's see how a graph would look in that case, right? So typically, most of the corner detectors tend to operate on grayscale images because there's a lot of information in the grayscale to find out the edges. So the first part to do is you want to create a graph, like VX graph is the kind of data object that's in there. So you want to create a kind of a node that takes RGB image and gets you a grayscale image, right? Just kind of one part of it. Now, if you try to see the grayscale image, that image is not something the application wants to access. All application wants to do is the key point. So you can simply say it's a virtual image. So you're telling the implementation, OpenVX implementation, that I'm not interested to access this buffer, so if you want to do any optimizations, go ahead and do those optimizations, right? And once you have the grayscale image, you simply say, okay, I want to run Harris corner, so you instantiate one more node into the graph, and which basically completes the whole chain from input to the output. We're going to look at some other example. This is kind of very simple. So if you want to take key things here is this VX context is one, and there's a graph object is another way to kind of abstract. You can have multiple graphs inside a context, and you can have multiple objects. All objects stay within the context in there, right? And here is another example about convolutional neural networks. Tomer is going to cover a lot of details into this one, so I'm going to just briefly mention this is a picture that I stole from AlexNet document. So you can kind of, I just looked at one piece of it, just one piece, and you can see there are kind of 3 layers: convolution layer, activation layer, and pooling layer. You can kind of map one-to-one each of those layers into a node in an OpenVX graph. You can kind of see if you try to map the whole AlexNet onto OpenVX graph, this is how the graph is going to look. Tom is going to cover more detail. I just want to mention you that a graph such a complex can also be specified in OpenVX. Now let's see how easy it is to, in terms of API calls, how easy it is to map these nodes into C code. So basically, you're going to basically have a call. For example, in this particular case, VX convolution layer, just one call, where you specify in which graph you want to instantiate that node and what are the inputs to it. In this particular case, if you try to look at the convolution layer, it takes X1 as input, W1 weights as input, and the bias as parameters as inputs. It has a couple of other parameters, and output is going to be Z1. So it's just one call. You're basically specifying one node in a graph. And similarly, for any node in the graph, all you have is you specify what are the inputs, what is the output. Okay? You kind of allocate those buffers ahead of time, those inputs and outputs, whether they're temporary or actual inputs coming from the host, and you basically build a graph like that. Right? One more thing I want to touch upon before going to an example is now you can spend, you kind of see how to create a graph, but when you try to deploy your application, you want your application to be very small and you want it to run really quick. You want to be able to deploy it much easier. One way to do that is you have this deployment model where what it lets you do is you can create a graph and then you can kind of export that graph into some kind of a vendor-specific format, and Jesse is going to cover, and Terry is also going to cover some examples on that. I just want to briefly mention about the model. So you can kind of export a graph into a binary, and you can just deploy that binary so that when you don't have much of an overhead at the time of deployment, at the time of actual runtime in the field. What it gives you is the compilation time. What are the tools that a vendor has can be done offline. Sometimes it could be time consuming, right? And there's a lot of IP. Sometimes vendor may not want to distribute that, so there are a lot of possibilities in there. It also enables safety critical scenario there. So I'm going to touch upon a couple of the calls, how they look. There is VX create context is the call. Basically, if you want to create, you just have this VX create followed by what type of object you're creating. The call kind of all follows that kind of a naming convention. And for objects, all objects starts with VX underscore. If it's a context, it is VX underscore context, which is a graph, it's VX underscore graph. If it's an image, VX underscore image. So it kind of follows that notation there. So first, you need to start with creating a context. Using the context, you can create every other object in the OpenVX workload. So now let's look to see what are all various kinds of objects that are there in OpenVX. So if you try to look at a computer vision workload algorithms, you need to deal with a lot of kinds of objects, not just images. If you're trying to use neural networks, you need tensor objects. If you want even multidimensional, it doesn't have to be neural network. You could use tensors there. And some algorithms, such Laplacian pyramids or something like that, you need a pyramid, an array of images with some kind of relation with that. You can specify that. And like array of floats, array of integers, array of key points, you need kind of an array object sometimes when you try to do key for corner detector. There's lookup tables, remap, and scalar is special. Scalar is just kind of an abstract, like a single value, such as an integer or a floating point value that you want to constantly keep changing. We kind of abstracted it because sometimes you need a means to pass a value to a low-level hardware, and you don't have an access to a pointer or something. So we kind of had to create an opaque object to be able to modify those values. And there are these vision functions. We call them kernels. which are basically just specify what are the functions the current implementation supports. And OpenVX specification does mandate that every implementation has to implement certain kind of functions in order to claim conformant. And we try to make sure, like Frank was mentioning, for the low power devices, we need everybody to support those set of functions, especially the fixed point implementations. Some implementers might choose to implement floating point, but that is not mandated because not every hardware can support those features in there. In addition to the base functions, vendors tend to extend it with their own functions depending on the markets that they're going after. Typically, the process that way works is vendors implement certain functions, they come back to Khronos and say, hey, our customers are interested, and multiple vendors look at this scenario and say, we want to standardize it. It comes back to the standard committee. We try to add it to next revision of the spec. And in addition to the vendor extensions, we also have the API for user kernels, where a third-party ISV can use that API to build their own application, their own kernels that they can supply to vendor, or an application developer can build it themselves too. Right now, the user-defined kernel API, what we have is the host API, what Frank was mentioning, and we're looking into ways to expose other ways in such a way that we don't break the portability. We try to keep the portability as one of the key features, and the performance is the other key feature that we want to keep in there. Now, looking at the graphs, I think we saw one example there. I think two special things about the graph is, one is the nodes. You can just take a particular kernel and instantiate it and specify what the inputs are, what the outputs are. In addition to that, standard data objects, you can also create some kind of virtual objects, which are basically, you're telling the application you're telling the OpenVX implementation that I'm not interested to access from the host. So that means you can allocate this buffer wherever you want inside, right? It could just an abstract type to just connect between two different kind of nodes in a graph. And there are extensions. Not all implementations need to use these extensions. One extension is neural network extension that Tom is going to cover. Tom is going to cover. And then there is import-export extension that is kind of integral part of our safety critical. There are other extensions such as ICD, 16-bit. You can look at it on our spec. I'm going to skip that. So let's talk a little bit about data objects. How am I doing on time? 10 minutes. Good. So when you create an object, what application gets is only a reference to an object, not an actual object in there. And the way the OpenVX implements these references as a pointer to a struct, and OpenVX header files doesn't define what the struct is. It's up to the implementation to decide. What this lets you do is kind of a strict type checking. So you cannot assign an array object into an image object. So there's kind of a strict type checking happening there. And another feature that OpenVX has is this references. That means an application can allocate one, and it can give that object of reference to another, for example, a node. When it doesn't need it, it can simply release it. The implementation keeps track of the reference counting in terms of when an object gets used. When all the references are released, that's when implementation knows, okay, it's up to the implementation to choose to release it or recycle that buffer. That's kind of implementation specific use case there. So here is an example of how to create an image. So you're saying that create an image of 640 by 480 dimensions of RGB within that context that is passed. And you can see there is a VXDF image that's kind of an enum for various different formats. There are about 13 different standard formats that OpenVX supports. And you can kind of use that image. When it is done, you call VX release image. So one thing you notice is when you call VX release image, we're passing a pointer to the image. And one of the things that OpenVX does is once the release is successful, it resets that to kind of a null. So that way, it kind of invalidates that pointer. So when you try to use that pointer next time, you get an invalid handler there. Like I was mentioning earlier, it is kind of very strong type. That way, you cannot just kind of exchange. You cannot assign an array to an image. So kind of you get a lot of checking done in there. But they're essentially, basically, they're just a pointer to structs. And we have a feature where there are certain calls, such as VX get status, which can take any kind of an object. So that means you need a mechanism to kind of cast any of the object into kind of some kind of a reference. So we created this object called VX reference. which can kind of think about it as like a base class. You can kind of cast any object into VX reference and pass it to get status. And if there's any error associated with the object, it will kind of return you that error in there. And like I was mentioning, these are all opaque objects. That means if you want to access the data of a particular object, you have to explicitly ask the implementation. So one way is you can simply pass a host pointer and say if it's an image, you want to make a copy of that whole image. And you can specify the layout of your host buffer, and the implementation, the copy call will take care of copying it. Or you can explicitly ask saying you want to map or unmap. That means when you call a map and give an object, it gets you a pointer. It kind of copies it somewhere or gives you an internal pointer for access and gives you the layout of how the memory is organized. And the host can just kind of use that pointer to access it. When host is done accessing, it has to return that pointer back to the OpenVX implementation saying, okay, I'm not going to use that anymore. So once it gives the pointer back to the OpenVX implementation, it's not supposed to touch that pointer. At that time, it's the OpenVX which owns that kind of memory. The reason for this is, we have to deal with complex memory hierarchies. We have to support hardware going from DSPs, GPUs to even some fixed function hardware. And here is kind of simple ways to check the error status. So one thing I want to mention about is checking when you create an object, you need, instead of checking for null, you need to call this function called VX get status. So basically, in this particular example, you create a context, you call VX get status, you pass the context as a reference, check to see if it's successful or not. So you're not supposed to check for null. This is one thing different in OpenVX compared to a lot of other APIs. What this gives us is kind of a lot of portability across a different hardware in there. And there is log callback feature. You'll see that Tyree uses that in his example. And here is kind of various different calls that you can use to create different data objects. You can see on the top, creating an image. And you can see all these calls take context as the first argument and various metadata that describes what kind of object it is, the dimensions that are. And I just want to touch upon the last one, create tensor. You specify number of dimensions, in this particular case 4, specify what each type is. And there is a type, if you see VX type int16, so which is a 16-bit, and you can specify the fixed point notation, basically what is the fractional number of bits. In this particular case, it's going to be 8-bit fractions. And OpenVX does support 8-bit and 16-bit fixed point at this stage. Now, we talked about virtual objects. So virtual objects creation is going to be very similar to normal data objects in terms of context. Only difference is going to be virtual objects are they stay within the graph. So you specify graph as the first argument and you use the keyword VX create virtual image or virtual tensor. So that's a way to say that these are all intermediate buffers, and host is not going to be able to access these buffers. You won't be able to copy data in and out of these buffers. So here is a simple example just to show you the sequence of calls. So first you create a context, then let's say we're taking an image, so we have an input and an output. So you kind of use VX create image. In this particular case, we're creating 8-bit images, 640 by 480 size. Then we're going to create a graph from within the context, and then intermediate buffer. You can kind of see, so there's a function 1 taking input and producing an intermediate buffer, and from intermediate image to kind of a function 2 getting into an output. Whatever those F1, F2 are, right, in this particular case. You can kind of see F1 node. So you're going to see a lot of the functions with the name VX and name of the function. If it is Harris, it's going to be Harris corner node and things like that, right? And you pass the graph and the input parameters and output parameters. Once you're done building a graph, you have to call VX verify graph. So this is one opportunity where an implementation gets to look to see if everything is correct in terms of parameters. Is the graph connected? Are there any cycles in the graph? Things like that, because it has to be an acyclic graph. You cannot have cycles in there. It also gives an opportunity for an implementation to look at the graph and try to see what can it do to speed up the execution, and if it needs to do code gen or all the optimizations it can do. Once it is done, you just write the input image, call process graph, and then just read the output out. Right? Let's look at some of the built-in functions that we have in OpenVX. So there are element-wise functions going from image addition, subtraction, tensor add. You have color convert functions, table lookup, threshold, color depth. There are a lot of functions that are available, right? And there are filtering operations going from box filter, Gaussian pyramid, Laplacian pyramid. If you have LBP, hog, bilateral, non-max suppression, there are a lot of functions there available. My grouping may not be perfect when it comes to filters because I put hog and LBP kind of things in there too. And there are some geometry functions. You can scale, warp, and there are histogram, standard deviation, min-max, location. Can kind of look at it on our standard spec. Most of the useful features are here already, like some complex canny edge detector, Harris corners. I call them complex just because they're not straightforward image processing operations in there. And we also added in 1.2 some control flow where you can specify, let's say, you have two data coming in, front camera and back camera. Let's say, for example, you want to pick which one to run depending on some kind of a flag or depending on activity. You can use control flow features to be able to do that. And let's go back to corner detector example, the one that we see. In this particular case, we don't have a direct function to directly convert from RGB to grayscale, so we kind of need to go through some intermediate stage because grayscale is not a color in a sense. So what you do is you kind of take an RGB, you convert that to a YUV image, and you kind of extract Luma plane and call it as a grayscale and use that for your Harris corner detector. The fact that you specify YUV is a virtual image, U8 is a virtual image, implementation has a lot of liberty now. In fact, it can just fuse all these kernels into even the Harris corners. Harris corner starts with a kind of a gradient filter. So it can take RGB image straight into Harris corner, do the gradient in its own local memory, color conversion into its own local memory, and apply gradient in there. So all those optimizations are possible because if you specify them as virtual. If you don't specify them as virtual, you don't see much performance coming in because then it has to generate these buffers, intermediate. And how is the code going to look? You basically, for color convert, you simply call VX color convert node, specify input RGB, and the output YUV image. And channel extract, you simply say, okay, YUV image, I want to extract the Y channel into this 8-bit image. And then Harris corners, you pass the grayscale image, and then you kind of specify what are the different thresholds that you have, different parameters of the Harris corners in there. I'm going to rush quick because I'm running out of the time. So now that you know kind of how to build a graph, you got a feel about it. Now you need a means to be able to access this data in the image data objects, right? So you need to make explicit calls. So there is this function called VX copy image patch where you can specify which plane and what's the rectangle region you want. And you can also specify what is the layout of the memory that you have on the host, right? You can see some of the examples in our tutorials in there. So you just make a call. It basically takes care of copying it. And alternatively, you could also do map and unmap available for different kinds of objects. One thing I want to mention here that is important, I just want to reiterate, that is the ownership of the actual memory available in there. So once you create a buffer, the ownership of the actual buffer stays with the OpenVX implementation because you don't even have access to the host. When you call map, the application gets access to it gets the ownership of the buffer because it gets a pointer. When you call unmap, the application is not supposed to touch that pointer anymore. If you touch it, behavior is going to be totally unpredictable, just like any other. That's just like using a pointer after free. Okay. And then coming to the final one, all you do is once you build a graph, you just call VX verify graph, and then in the loop, you just process like the example that I've shown before. And there are a couple of other attributes that are available, tools, where you could query an implementation to see what is the actual time it took. So there are APIs called VX query graph or VX query image. You can query different attributes of these objects. So in this particular case, what I want to highlight is there's a graph attribute performance that you can use to query how long the graph took to execute. It will maintain statistics such as what's the average time. So you don't have to write the host code in there. That brings me to end of my presentation. Kind of I touched upon each lot of points, but I didn't go deep into it, and that's what next guys are going to do.
High-level question. Does the optimizer, when you compile the graph into the runtime, does it actually estimate the time for each of the nodes to compute and use that as an optimization for scheduling?
So as far as the spec goes, spec doesn't dictate any of that, but as real implementation would look at those considerations, right? So for example, if I want somebody to use my hardware, I want to make sure I get the best performance out of it. Let's say I have GPU and CPU. I would try to look at the workload and try to estimate how long would it take, how many resources do I consume. It's not just time, it could be memory, depending on what profile I pick, right? And I'll make a judgment based on that, and I use my own strategy for my implementation. For example, TI might use completely different strategy because they have a completely different system.
Implement their own version of the compiler as well?
Yes, yes, yeah. So that's the beauty about it. From an application perspective, you're just giving the end-to-end workload. All the problem now lies with implementers to figure out how the heck they can get the best performance out of their hardware. And the beauty of this is, from application, you don't have to worry. Your code gets portable across, and you get the performance portability. That's key thing too. Right?
That step is done in verify graph. Which step is this optimization done?
So verify graph, as far as the spec goes, it's just meant for checking the validity. But since that's one place where an implementation get a chance, an implementation tends to put, all the implementation that I know of, tends to put all their special logic into verify graph. That's kind of a trigger point.
Cool. There was the verify graph, which at runtime it executes that command and processes it. Is there a way to, I guess, save that and load that, like a binary of it or some sort instead of?
Yes. So we have Jesse and Terry is going to talk about that particular one. So we have the deployment model, that slide that I have, where you just verify graph. That means there's a lot of compilation that happens. Somebody could even generate the C code and then generate assembly out of it, generate a binary out of it. And you can just export that binary, and you can just deploy that binary.
Do you have any standard performance graphs that you can show that the OpenVX implementation of a common set of routines, at least within a few percent of a...
Between the companies. So I would defer that to the last presentations because we have 6 implementers who are coming and presenting their data. I have a feeling that they're going to talk about how best is their implementation because they want you to use their implementation, their hardware.
Also the question, I don't know if it's best addressed data, but so is there a facility to store the graph?
Pardon?
Is there a facility to store a graph?
Store a graph?
I mean, it seems to me like whenever I invoke that call, the actually compiling optimization is happening. And so when I have a graph, I can probably process it multiple times when I have new inputs. But definitely at the time when I'm invoking it, compilation is happening, and that might be very time consuming. So whatever is happening there. So what if I don't want to read ADFR? What if I only want this to happen offline?
Offline, yes. So I think we're going to talk about that. Yeah, we're going to talk about that. Sorry, he was asking.
So the question is how flexible the system after this verify happens. So in the loop, do we have the possibility, for example, to change the parameters of a node?
Yeah, good question. So we debate aloud about that too. So typically what happens is if you have different images with the same kind of metadata, you can pass different objects into it, right? For example, let's take a graph. Let's say you're not changing anything functionally in there. Let's say if you want to change a filter size from 3x3 to 5x5, or from 5x5 to 9x9 Gaussian filter, for example. Sometimes that may trigger a different logic as an optimization. Sometimes if it's 3x3, I might use one hardware. If it is 5x5, I might use different hardware. It depends on the implementation there, right? So there's some decisions made. So the way we crafted these kernels is parameters which are kind of, we agreed that doesn't require recompilation in most of the cases. We try to expose them as opaque objects. So the fact that it is opaque object, that means you can modify those parameters, right? And also you can modify the parameters in terms of the value of the particular opaque object, or you can attach another opaque object with the same metadata. Same metadata means if it's an image of 640 by 480, you can just attach another object with 640 by 480, and it doesn't require any recompilation. Now, Frank, Jesse, you guys want to add to that? Later, okay, yeah, we're going to talk about that later, yeah.
If VX process graph, blocking or non-blocking function.
Okay, so we have two sets of APIs. VX process graph is a blocking one. We have another two functions called schedule graph and wait graph. Schedule graph is non-blocking, so you can say schedule graph, do whatever you want, and then simply say wait graph at the end.
Okay. Yeah, let's say if I have a very long processing pipeline, is there any way for me to interrupt during the execution?
Interrupt during the
For
execution.
example, if the function call for some reason takes too much time, or I have some other tasks to process, is there any way for me to cancel the execution?
Cancel the execution. From the spec, we don't have that feature at this moment. Maybe if you have a particular use case, I think I would love to hear that. If you could post it on our website, or just maybe we can talk offline. We'd like to get that feedback. Thanks.
So you showed the create context function, but you didn't pass any parameters at that time. Is that the function that where you would say specify what I guess SDK or what runtime device you're actually wanting to run it on, and can you run on? Can that context have multiple devices within it, or is it just at compile time single device?
So context is specific to an implementation, not device, right? Within the context, you can have multiple devices. We have debated extensively on how to expose devices. We could not come to an agreement on that specific thing. Reason is, we have from DSPs to, GPUs, high-end. We're still trying to figure that out. How do we expose devices? But in terms of different implementation on the same hardware, we do have an extension called ICD, installable client device. So you can using that API, you can pick, if you have two implementations on the same platform, you can pick one of that.
So we added the neural network extension to OpenVX. And what we have here is that we think that OpenVX is very good for neural network in terms that first it already has a graph formalism inside. So it can bring the neural network into the embedded environment. And if you look at the thing, then we say the layers of the neural network can be represented as node in OpenVX. And we need an object which is what neural network needs to work with, which is a multidimensional tensor. So the nodes are connected with this multidimensional tensor. And we added also types of layers like convolution, activation, pooling, fully connected, and softmax. And what's nice about OpenVX also that we can also mix them with normal nodes, that we can do normal computer vision with normal traditional computer vision and also neural network. What's also is that most of if you get an image and you know what people do with neural networks, they usually move it into something float in order to start. So you need to do some conversion even to images. It's not that you run neural network as it is from the camera. And OpenVX gives you those capabilities already inside. If we look now at there, someone talked about it, that there's also an import and export extension in OpenVX now. We talked about later. And it allows, because the weights are very big, it allows you to actually, if there's some optimization which is done on the weights, you can offload the optimization by doing like offline compilation, and some compression was done, and then you load it with an import weights which are compressed. This loading can be, we go into the import-export extension. This loading is not mandated to be in something which you don't have to have a file system. It's very general, such that it can be run on many kinds of hardwares. And as you said, 1.1, the specification is provisional, and we released this week specification which is not provisional, it's for 1.2, which also had support for U8. And we welcome now that we see how people get and adopt. And so we look at that overview of what we have in 1.1. So we say that we supported Q78, 16-bit integers. And it's not that we support all those workloads. Those workloads, we have all the ingredients as layers, but you also have user nodes. And because you have user nodes, you actually can extend it. So we expect that the things, those are very, those workloads using a very general blocking blocks, very general blocks that people will use, but it will be in combination with some extension which the algorithms and the one who wants to have their own specifically special way of doing neural networks. Now if we go to 1.2 features, as I said, we moved core into the core specification. It will support more vision function, classical vision function. And neural network is an extension. That means not everyone will support it, but we hope that it will. And we have two variants of the tensor. Well, we have two variants of we created it actually into two extensions. What is 8-bit only extension, and the other one is 8-bit with 16-bit extension. That means some vendor will support, they say, you query a string from OpenVX, and it tells you what kind of extension it supports. So if it supports only 8-bit, you'll get a string, it supports only 8-bit. If you get a string which is 8-bit and 16-bit, you know it supports 16-bit. It allows in 8-bit for people to have very, very low power implementations. So those extra data type in U8, in 8-bit is U8 and S8, which are very well used for a very well-known algorithm, GemLoP, which is used by TensorFlow, and the quantization is there, and Ristretto, which is used in Caffe. And we add some more built-in block of layer, like for faster RCNN and fully connected networks.
Sorry, so you mean 8-bit with 16-bit is a mix of 8-bit and 16-bit, right? You support a mix, right? That's what you mean.
Yeah, I mean I support a mix of them, yeah. Okay. So we look at the convolution neural network, and we have those layers which Rada talked about, and you can see that it's now split. So because it's split, how it's done in OpenVX, this split, you can see that you have a box at the top and box at the bottom, and for that we actually, and that's why we have, you can see that it actually twice, and then at the end you haven't converged. So it's a good example to show some of the feature we have in Tensor. So what is Tensor? So it's a multi-dimensional mathematical object. Example is matrix is two-dimensional. And currently, because of hardware, because we really think about hardware, is the minimum which we must allow any vendor to support is 4 dimensions. Some vendor can decide to support more. And then we talked about this merging and splitting of tensors. So we added the notion of U, that you actually, we do everything. You see the edge of the data, everything is static. We try to say, to create things actually really define very good in the spec, what is static in computation and what is dynamic in computation. And the data in that case is static in terms that its definition of how it's going to be is going to be static. So even if you optimize it away that it's virtual, still you represent how it should look like as it was in the memory. and that will help lots of embedded system, because then you know exactly where to put your memory into and where to actually load it back. So instead of using normal thing, which most of the framework we're doing, you just split and cut. We use here view. That means we create the object of the full object of everything together, and then we break it out into several views, and we take those views and give them into exactly the layers, the nodes, which actually drop down the memory into those places. I want to go back again about this slide, and you can see exactly how it goes. So the first one layer is 5 by 24, 224 by 224, and after that, it goes into an object which is 96 by 55 by 55, and it's split into two. So you actually, now you create two views of it. You take this object of 96 by 55 by 55 and now create one object of 48, 55 by 55, and another object which is 48 by 55 by 55. And then you'll see that actually now the network is starting to work on each of them individually. At the end stage, when you go to the last, almost the last stage, the last of the box, you recombine them together. So again, you create an object which is 256 by 13 by 13, and you split it into two objects which are one is 128 by 13 by 13, and now they become to be again one object, and then you can give it into the next layer, and from now on all the layers are not split anymore. So we have another thing which we have, the last is the interaction with the images. As we said, we wanted to work with images and actually to work with normal computer vision. So we have some conversion which can be interpreted as a cast, but it's actually using this view mechanism. It's actually creating from an image, for instance, if it's three-dimensional image, then you have creating three different views, and actually creating from each of those views an image. And the interface of it, it's we call it create object. I would say create image object array from tensor. Okay, so now we're looking now at the code. So. And the code is there on your machines as an example code. Let me show it even running. So you can see here that I'm creating. Sorry, I need to remember not to move too much. And always you see that we created as an input for AlexNet a tensor of 3 by 227 by 227. This is the input. And we created an image object array from it, which is the input in images. And you can see that then we do some pre-processing. I'll go to it later in more detail. This is a graph. It's actually you implement a graph in OpenVX. So you can see that you actually get the input of this image. And from that is outputting into those images of actually where a tensor. Their view is in the tensor. Okay, so how is done the pre-processing? This is an example how to actually take images from a camera and prepare them for AlexNet. So what they were doing here is just subtracting scale. So subtracting by an offset and multiplying by a scale. And they are used also in training, so they are constant. So you can create a pre-processed graph. So you can see here the nodes. It's for each image, so we can size them to be only see the through, which are channel extract, convert bit depth, and subtract node. This is done because the convert bit depth also have the scale inside, so it's already there. And we actually scaled the offset with the scale before, so it became to be very short preprocessed graph. You see here, after you create it, preprocess, verify. That you don't have to actually make it as a graph which is only alone. You can actually run completely after that neural network, but for the example, it's a good example to show the feature. I don't remember what I wanted to put here. Okay, again, example. This is AlexNet. It's a long network. You can see with all this information which we gave, it's a long network. It's even if you saw in the previous page, there's many ingredients. So there are many layers. So it becomes to be a very long code. So what do we do? So what we have is to do some auto-generation. And we'll go over later on the example and show everything working. So if you go to this auto-generation, what happened is auto-generation is that we released in Intel, I'm working in Intel, we released in Intel a week and a half ago a tool. A tool inside, we call, well, there is one of the tools in CV SDK, which was shown at the booths yesterday and the day before. This what tool is doing is taking models which were pre-trained in Caffe and TensorFlow, and in the future there will be more support for more frameworks, and it convert them into OpenVX.
That's already been released?
Yes. It's released as a beta, but it's out. You can download it and you can download it, and in the README file you have the instruction how to download it and install it. Okay. So this model optimizer from Intel is an hour, and I think now from this point I want to move out into the VirtualBox and show you how it works and how this code is looking at. So, by the way, this is how the code looks after you generate it automatically with the model optimizer. You can see we have lots of functionality in OpenVX, like assign node parameters, and there is also create node by name. So it allows a lot of auto-generation tools to be working with OpenVX. We in this SDK, we also have a tool, a graphical tool, when you actually put a graph in a graphical way, and you put the bash in, and it creates for you an OpenVX code.
There's a text file called AlexNet preparation, I forgot the name of it, on the USB. If you copy the files, that's the one that Tom is referring to as readme.txt. That should have instructions as how to generate this whole code, all the exercises that he prepared. You have all the instructions in there in terms of how to download the SDK and how to do that, all the steps.
Okay. So this one terminal some.
This is an Intel tool that takes a graph and generate OpenVX code.
Yes. So it takes a Caffe model.
In that case,
Caffe model and generates OpenVX code that you can use in the lab.
Yeah. So in the VirtualBox, the code I was talking about, the sample implementation.
Running on which processor?
OpenVX. Any OpenVX it can run.
Yeah, the underlying hardware is that Lion, Phi, or what?
Okay. This is OpenVX code. That means it can run on many hardwares. Okay, you ask what support do we give and actually running it optimized. You need to go into the page and check out exactly what hardware is supported. Okay, but in general, it can support any hardware. It can also support other vendors' hardware.
Yeah, no, but this is tool from Intel, so I just wondering what is the underlying Intel hardware that is possible.
Okay, I can. Well, in the demo, they showed it on Skull Canyon. So definitely, this is one of the hardware. So it was demoed here, running. They showed a demo of running, calculating orb features, and do transformation to a car in real time, and then also put some neural network extension of SSD network, which is recognizing pedestrians, but not pedestrian objects. Object can tell them what's the name of the object. So this is a laptop, this is a human, this is, and put the box. So those are those two demos which were shown here this week. Okay, so in this VirtualBox, the first thing I want to show you that we installed here a folder which is called CNN Neural Network Demo. So in this folder, there is an installation of OpenVX with this extension in the bin file. And in this bin file, we can run the CNN sample, which is the example code which we put here. And that code could contain more than AlexNet. It also contains, but we don't have the weights for it. But here in the example, we put weights only for AlexNet, but it also contained for overfit, implementation for OpenVX for overfit, and implementation for OpenVX for GoogleNet. And I'm giving it the image. I'm giving it the weight file. Currently, it's not really used. It's just those weights which are used to do the pre-process. And I'm giving it another. But this, you see, this is something very vendor specific. It doesn't have to be. Each vendor will use this layout, those weight as it is, and the way they are formalized here. Okay. Okay. Maybe Rada can help. Maybe I'll put it as a terminal. Terminal, I think it opens better.
Is the font size?
Yeah, the font size in the terminal.
Okay, go to the terminal, then let's see. Oh, let's see. Let's say view.
Okay.
Is it better? Yeah. Okay.
Okay. And I was running CNN sample app. And I added an image. This is for the scaling, actually to do the pre-processing. Those are the weights for the training, and the last thing is just for enable this to show really what we defined, a conversion between the probability, what's the index, to actually what's the name in it. So you know exactly what it is. So you'll see it running, and here it's running non-optimized. This is the sample implementation of Khronos, which it's not. This is something which Khronos have and use it to build the conformance test, and it just meant to show the functionality. There's inherently, it's a sample implementation and not a reference implementation. It means that inherently in it, it's not optimized because we expect other. And you can see it runs in OpenVX, and he actually found that in the picture he sees a collie. And you also see that You also in the scope you see that there is a sheepdog here, but it's a bit less probable than the collie. But it's still, you find out there's two things in this picture, which is the collie and the sheepdog, which is the same. So this is a good example. So now we go to this auto-generated code.
There's a script there called Run Alex.
Good, which you write. You put it where?
There, if you type ls minus l.
So question, in terms of actually implementing
Yeah.
this sort of bigger piece of
Run alex
code,
dot sh.
Yeah.
Is it in USB?
Yeah.
This is in USB.
Yeah.
Under which direction?
Okay, so this is a what you have on the USB is a virtual machine. So you have to install VirtualBox and run this, load up this virtual image, VM, and then run the Ubuntu on it. Then you can access all this. So there's a README install procedure. There's a README that gives you all the steps how to do that. And the command that Tomer has typed, he remembers it very well. I don't, so I created run alex.sh, so that has that command line.
are we going to spend time today talking about best practices for OpenVX design, code design? In other words, like following this question about multiple graphs. So this is one graph. I could have multiple neural nets and business logic. And if I want to, do I make one massive code that I just put on, that I just let run, or do I build, pre-process and compile these graphs, and then write C++ business logic around them, and then, so what is the actual implementation for using these pieces as components in a larger piece of code?
Okay. So in the larger execution, those pieces are, you can run it. We try to make them actually in one graph, but I think to put them in one graph is a very hard task. So most of the time you'll have a graph and you'll have some logic around it, which runs several graphs with some logic around them. We try to do something in 1.2. We put a select, which says that the graph can actually select to go one direction and not the other direction, which make things more statical, and you can parse more things as graph. But still, the option of actually be able to do everything in graph is impossible. So standardizing everything is impossible. So you'll need some logic around it.
So there are kind of like design things just to follow. So if I think that I'm going to act on the same piece of memory, I should probably keep those graphs together and move them over. Because once I pre-compile these graphs, I can probably move them off the processor and
Exactly.
back on.
Yeah.
So if they're going to act on the same thing, I should probably have some business logic that just stays there with a bunch of graphs.
Yeah. The thing is also it allows, there is a business, some logic, but we're thinking about also always on applications, where you actually put the application fully to run as a graph in always on mode. So you actually want to actually parse the graph and then just give it and run.
Are there limitations to the structure of the graph? Like it has to be just or for the neural network, pure feed-forward network? Like it can't be ASIC, it can have like recurring, or the recurrent, like I saw the recurrent neural network was on a list on one of the prior slides, so that's supported where it can internal to the graph feed backward to the beginning?
Yeah, you can do it, but running several times the graph. That means, there's a limitation in the graph, which it only goes forward. But there is some capability of actually, we call it delays, in which you can actually say that part of the graph is actually is going to change in time. So you can create something like, I'm going to run it 3 times, so I create a delay of 3, and I get actually the objects multiply 3 times. And then when I run it first time, and the objects is in index 0. Second time it's 1. Third time it's in 3. But when I use it in the graph, I tell him exactly which one I want from that at the time, which one I want as the index. So in that case, each time I run, I just use it as a cyclic buffer. I just change the values. the objects actually. I changed the objects such that you can each iteration enter maybe the previous iteration or a new input.
Would you happen to have just an example maybe later that you could provide like a link to of exactly how that would work, like some code to show that?
At RNN. I don't have it here now.
So is the question specific about how to use multiple buffers, or is it specific to using delay?
Yeah, this is a good question. If it's delay, I think we're going to have something. Yeah.
So the example that Terry is going to give, that source code, he does have a means to be able to use multiple buffers. So you can kind of, there's something called a swap buffer. So you can create an image object using a host buffer, and then you can basically say, let's say you have data coming from a camera, you have data buffers coming from a camera. You can simply say swap handle. All it basically does is it makes the image to use the new memory pointer that was passed, and you can kind of have multiple buffers managed at a top level. You can kind of keep feeding one at a time. That's one way. Other ways, what Tom is talking about, you could have a delay. You kind of manage the delay buffers inside. There are two different ways of managing. So Terry is going to talk about the swap handle stuff. You'll see that again.
Well, I'm not really going to to talk about this because my talk will be more about import-export. But after this tutorial, maybe people can take a look at the code.
Okay.
Because indeed, in the code, I'm using both delays and images created from handle. But obviously, I will not have time to go deep, to explain these features that are the base feature from OpenVX. But there is an example in the code.
I'll be here if you're interested. I could just go over that and explain you all those pieces. Yeah, we have 3 people, so 4 people.
Some simple example show how the graph work and how they got translate how the interaction between work and what is all these. You have different nodes, right? They are connected by the node in the graph. So how's the data pass from one node to the other? So that kind of thing is interesting for us. Okay. Go to Alex and then brought 2 big pieces of code to learn from.
Okay. So I can help you with that. So there are a lot of online resources for that particular.
Okay. And next thing in the example, I want to show the generated code. Okay. In this directory, we have binaries, which are the weights which are generated, the conversion of the binaries of all the weights to move into to the quantization. In this case, it's Q78 from floppy disk. They're already moved there. And it was used, and also there's a folder which is generated code. And this folder of generated code is actually what you see here. We created here a code, and there it also contains a build shell utility to build it. So after this generated code was out, you can actually run it. The only thing you can see here, it's like there is graph process, which is here. It's more code to actually connect everything together. You can see that actually it's hard-coded the image. But you have also graph C and graph C, which is actually connecting the code itself. We generated, actually, this is the major code of moving it, and everything else is just wrapping around, making things work. So at least you can take that, and this is your actual graph which runs, and you plug it in into your code. So in that case of code, it creates a binary, and I move it into the binaries. And okay, so you just and I'll put here something so we can look later, because here it's it just dropped all the information out till it will come show in a few seconds.
In the event that we want to manage multiple graphs, are these separately executed? Do we use some kind of inter-process communication to coordinate?
Sorry. No, it does. Okay, it worked. You haven't installed library? I haven't installed. Okay, why don't you answer this question? Okay, sorry, the questions.
Well, yeah, I'm just trying to figure out, I'm looking on the web now for best practices for implementing stuff. And I can dig that these are little binaries that get built. And then my question is, if I want to, as a larger level developer, I'm moving these things off the processor, and if I have multiple in place as binaries, do I have inter-process communication to manage data flow and communications between them? How are these actually managed as separate chunks?
Okay, so if they are in the same graph, then actually its implementation, if it's outside the graph, so we have in the import-export, and we have something we call create image from Intel. We currently standardize one kind of memory type, which is host, and we left everything there open. And that can be changed with more possibilities, like say, actually the memory is in the driver, the memory is in the camera. So actually, what you say, okay, I created some object, but it's not existent on this accelerator. It exists on a different one. So when you compile, it knows that you need to use a special hardware like a DMA or something, some communication device in order to get the data.
So is the OpenVX in general thread safe? I mean, if you have two independent thread running parallel, right, and running two different graphs, okay, but the command line hardware is the same, right? So they all try to access the one common set of hardware. So does the OpenVX runtime try to manage that? How does that work?
Yeah, that's so. Thread safety is not something the specification defines in terms of the use case you're talking about is you have two different graphs using the same object as input.
Well, it's two tests running two different graphs, right? So from the thread point of view, they are just still in one graph, right? But eventually, all these graphs going to be accessing the same hardware and the same memory, right? Okay. So I'm just wondering, does the OpenVX runtime, right, will try to manage that, right?
Okay.
So as if a possession is running parallel, but in reality, right, you have to serialize.
Yeah. So that's implementation specific. So different implementations might do differently, but I think all implementations will try to achieve the best resource utilization, right? You try to schedule two graphs simultaneously, and there's only one hardware. At some time they have to serialize. They're gonna give you completion eventually, and how they optimize and manage is kind of very implementation specific. So there's no one answer for this one, right? So the specification cannot dictate that. Yeah, it's implementation specific. But what specification tells you is, say, if you do schedule graph, and you say weight graph on those graphs, when the weight graph is done, you get the results. Now it's in the best interest of an implementer to make sure it does the best resource utilization. That's the whole purpose of this. So what is the API that we can agree on? All implementers are going to try to squeeze the best performance the way they want. The danger of specifying something at how a device should be managed is now it may not be portable. It means the specification cannot be implemented by everybody.
But the application, right, where you do need to run two graphs simultaneously.
Let me give that to Frank.
I just had a comment on that, in that if you're making these two different graphs and you want to sort of launch them simultaneously, as Radha said, the system will do its best. But because you didn't tell it necessarily ahead of time, you're going to try and run both of these graphs at the same time. Its best may be suboptimal because you sort of, it's runtime having to make these decisions about where to schedule things. You could make your two graphs one graph. It doesn't have to be connected, right? So if you make your graphs be actually put into one graph data structure and ask it to do the verify graph, then it can actually do a lot more in terms of how do I interleave these two processing streams. So it's one thing to consider.
So basically, you take two graphs and put them together and call it one graph.
Just call it one graph.
And
Yeah.
you get like maybe 3 pair or what?
There might be, there's nothing in the spec that says the graph has to be connected. Like, as in, there can be pieces where that are independent from each other.
But you still allow connection, right? Even if
Oh, yeah,
say
you can
want
connect them if you
interconnection between
connect
two
them via,
graphs.
say, some image, but they don't have to be connected.
Right.
And if you have these two connected, or, well, maybe they're different processing streams, but you want them to sort of run at the same time, and you want them to be scheduled in an efficient way, you put them in one graph, even though they're two different
But then we're
parts.
going to need his question about exiting early from particular graphs in the event that they are long running and blah, blah, blah.
Yeah,
I mean,
yeah.
we need to kill a process, basically.
Yeah, so I actually, I filed a bug. I went to the Chronos website, and based on the question about killing a graph, I filed a bug. So we'll consider it for 1.3.
Great.
But that's not going to help the thing that I just described, because you only have one graph handle, right?
About this, if you have, like you put these two graphs in one graph, so can you, for example, once you run only one part of the graph, in the next iteration you need to run both, in the next only one. So can you make it run only a part of the graph? For example, you only need this output, and then the OpenVX system decides which operations it needs
So the
to run.
way that I would do that would be to copy the graph. I'd have a version, sometimes I want to run it by itself, so I'd have a version of the graph with just that. And then I'd have another version where it's paired with the other thing for the times that I want to run it together.
So you cannot really control, or OpenVX cannot really decide in runtime which operations to run. So if you define a graph, it runs all operations.
Yeah, it runs it to completion.
But are there wait conditions or futures that you can set up so that if one portion of the graph finishes its cycle first, it can essentially switch out and stop?
So there's actually callbacks that you can stick on a node where it can look at some
And it's
condition
event-driven.
and abandon the graph.
That's a quick fix for the exit. Great.
You want to ask?
No, I just want to ask it. Sounds like the OpenVX doesn't handle like the concurrent execution toolbar. It's not like the scope of OpenVX. Based on what I heard so far. That's after the outhouse or some other.
You could just one thread.
OpenVX does not specify how to run concurrently or anything. All it specifies is you can schedule multiple graphs. You can wait for multiple of them. How it gets executed, OpenVX does not specify. Concurrency, the word concurrency is not defined by the spec.
But you can launch multiple graphs, as we said. My only point was that if you launch multiple graphs at runtime, then you've taken away some of the opportunity that the implementation has. And maybe somebody has a super smart implementation. I'm just saying that when we design the OpenVX API, we design it looking at how the implementation is going to be able to use the information you give it. And so if you give it all the information up front and you say, I'm going to run these two graphs at the same time, it has this opportunity offline to do some optimization. And if you just build the graphs independently and online, you run them both at the same time, there probably is going to be there's going to be some suboptimal probably scheduling unless somebody, again, the implementation will be super smart, but I'm just saying practically it's probably going to be less optimal.
So that's a legal graph. You have two graphs that's disconnected. So they go from input to output, but there's no connection between two graphs, and that's still a legal graph for the OpenVX. I mean, you do the run and verification, but I tell you that's an illegal graph.
I think we're getting. I don't want to hijack that.
Okay. We're getting up to a break.
Yeah.
I would like to finish this one. We'll
Yeah.
continue this one during the break.
Yeah, I just wanted to show you, still with the code, that just to see, to understand what's the output, and you can see that you have in each class, if it finds something, that means each index, it means an object, a name object. And you can see it's the same one, and 231 is the dog, and you'll see it popping up. Okay, so this is the output. Yeah, so it's more like It's not as prepared as the other code as a demo. It's just a generated code. This is what you get. This is the default which you get from the generation of code, which is called the tool is model optimizer. So that's, I think, finished this tutorial, in this session of tutorial.
So
You wanted?
yeah, there's a question about some hands-on examples for how to run some of these graphs looking at the low-level API. So in the past, we've been using one tutorial that I got on GitHub. So if you kind of Google, I just want to show you that website. We can discuss during the break. I just want to mention. If you just type OpenVX tutorial, let's see. Yeah, the first one is a GitHub page. Let's see if this comes up. So on that GitHub is what we've been using at all the previous tutorials at electronic imaging. All the source code is here. You can go to wiki. And this gives you hands-on tutorial in terms of you want to, how to compile a graph, and it goes you step by step, very detailed about actually running. If you want really hands-on, trying some, it uses AMD's open source implementation. And this tutorial, we try to organize it differently because we wanted to cover a lot of features, in-depth features, means like kind of neural network, complex features. That tutorial goes very much into just how do we read image, how to write an image, how to create a graph, how to run a graph at that level. And we felt this will be more valuable because we already have that one done. It's already on GitHub. You can do it.